Speeding at sea, it's me, Z. Welcome to the fourth video in my special relativity series, where we'll dive into the light clock example. I've received tons of questions about how the light clock works, so I actually decided to create a whole video explaining it. This is also how we derive the Lorentz factor in time dilation and length contraction, which I covered in the first video, so be sure to check that out first. Feel free to click through the timestamps below. Let's get started. Let's first begin with Einstein's postulates. A postulate is an assumption that is used as a basis to build a physical theory, and we test these by comparing the predictions with observations. Einstein introduced two key postulates that laid the foundation for his theory of special relativity. The first was the principle of relativity. This states that the laws of physics are the same in all inertial frames of reference. An inertial frame is one that is either at rest or moving at a constant velocity. This means that no matter where you are or how fast you're moving, the fundamental laws governing physical phenomena are consistent. There is no preferred frame of reference in the universe. The second postulate is the constancy of the speed of light. According to this postulate, the speed of light in a vacuum is always the same, roughly 300,000 kilometers per second, regardless of the motion of the light source or the observer. Now, this was a revolutionary idea because it contradicted the then accepted notion that the speed of light should vary with the motion of the source or observer, similar to how the speed of sound changes depending on the movement of the source and observer. Now, for the first law, I mentioned this idea called inertial frames. These are viewpoints that are at rest or moving at a constant velocity. A good example of this is, imagine you're sitting in a train, moving smoothly on a straight track at a constant speed. From your point of view inside the train, it feels like you're completely at rest. You can walk around or pour a drink just as you would if the train were stationary. This train is an example of an inertial frame. Now, if the train starts accelerating or decelerating, the situation changes. It is no longer an inertial frame because you would feel the effects of this change in motion. Einstein's first postulate tells us that the laws of physics are identical in all inertial frames. This means that whether you're conducting an experiment in a lab on Earth or smoothly cruising on a spaceship, the outcomes should be the same as long as both are inertial frames. Now, to truly understand the impact of Einstein's postulates, we need a clear and intuitive example. So let's explore the light clock, which is a simple thought experiment that illustrates these principles and the nature of space-time itself. The light clock consists of two mirrors facing each other, separated by a distance h. A light beam bounces back and forth between the mirrors. If we are observing the light clock from an inertial frame where the clock is at rest, then the light simply travels a straight path up and down between the mirrors. But things get really interesting when the light clock starts moving at a constant velocity relative to you, a different inertial frame. Let's say that the light clock is now on a train moving at a constant velocity v, and we, the observer, are on the ground. Let's first draw the mirrors with one on top of another, which is called a transverse light clock, because the light is moving perpendicular to the direction of motion. We see the clock moving to the right at the constant velocity v. But now from our perspective, the light beam isn't moving up and down, it travels a diagonal path, as the mirrors are moving horizontally while the light is bouncing between them. But we know from Einstein's second postulate that the speed of light must be the same in all inertial frames. The diagonal light beam seems to travel more distance though. What's going on? If we were in the same inertial frame of the clock, we would still see the ticks happen as the light bounces at speed c. Let's say that t prime equals 0 starts here, and we get t prime is equal to delta t here. If we were outside the train, on the ground, we would see that the light would travel at speed c, but needs to travel a lot more distance. More specifically, we can use Pythagoras' theorem to calculate the extra distance that we've traveled. We can calculate the distance half d, which is half of the total distance traveled or when the light hits the top mirror from the bottom mirror. we can do half d squared is equal to h squared plus v times t prime divided by 2 squared, since half of the time has elapsed in the clock's frame. So if we were to solve for the total distance that the light travels d, we would get d is equal to 2 times the square root of h squared plus v times t prime divided by 2 squared. So this is just from the Pythagoras theorem. We can use our simple kinematics equation now. Distance is equal to velocity times time, but now using velocity as the speed of light c. We can input the distance that traveled when we saw the clock move. And we get that each tick is delta t prime is equal to 2 square root of h squared plus v times t prime over 2 squared divided by c. Okay, that's a lot of mumble jumble math. Let's actually simplify this into a form that we can actually identify. Let's first distribute the 2 into the square root, and then undo the square root, group the delta t prime squared terms together, and then we can solve for delta t prime to be 2h over square root of c squared minus v squared. Now this still isn't quite intuitive, so let's actually take out the c here. So you might recognize that 2h over c is the original time of the clock if we were in the same inertial frame as the clock, because the light bounces at 2h distance with speed c. So we can actually replace that term to be delta t, the original time of the clock, if it were at rest relative to us. So our final result would then be delta t prime is equal to delta t over square root of 1 minus v squared over c squared. Now this additional factor might look familiar. It's the Lorentz factor, gamma, that I first mentioned in video 1 of this series. What this means is that for each unit of time in the moving frame, the corresponding time in the stationary frame is given by t prime is equal to gamma t. Gamma must always be greater than 1, because the velocity of any object must be less than the speed of light. The smallest gamma that we can get is if the velocity is equal to c, the speed of light, which then gives gamma is equal to 1. If we have any velocity that's smaller, like v is equal to half times the speed of light, then gamma will be greater than 1. So that means for our light clock, multiplying the original delta t by gamma gives us the time that we would perceive on the ground as the clock is moving on the train. Essentially, delta t prime, the time interval in the moving frame, is dilated or stretched out compared to the time interval in the stationary frame. So if you're on the ground watching the clock on the train, you will see that the clock is ticking more slowly compared to if it was at rest with you. This is the essence of time dilation. Moving clocks appear to run slower when observed from a stationary frame. Alright, now let's explore another variation of the light clock. This is the longitudinal light clock, where the light beam is now bouncing along the direction of the motion. Again, let's imagine a train moving at constant velocity v relative to us, a stationary observer on the ground. Inside the train, a light beam is emitted from the back mirror, travels forward to the front mirror, and then reflects back to the back mirror, with the mirrors now separated by a distance L. So let's first think about what happens at various points of the light's motion, including when the light leaves the leftmost mirror at t prime is equal to 0, bounces off the rightmost mirror, taking ta of time, and returns back to the leftmost mirror, taking tb of time. The total time elapsed, delta t prime, would be ta plus tb. At t prime is equal to 0, the light leaves the leftmost mirror, but the mirrors are moving. That means that as the light travels to the rightmost mirror, it would have also moved a distance v times ta to the right as the train moves. Now the light needs to bounce off and return back to the leftmost mirror, but the leftmost mirror has also moved with the train, a distance v times tb. So the light arrives back, but at a mirror that is now moved a little bit to the right along with the train. Alright, so would the time that we measure now be even more different than from the transverse light clock? Let's break this down segment by segment. As the light travels to the left, it travels at c times ta is equal to a distance L plus an additional distance v times ta as the rightmost mirror moved with the train. Then, when we return back to the leftmost mirror, we get c times tb is equal to L minus vtb. With these two equations, and knowing that the total flight time of the light, delta t prime, is equal to ta plus tb, we can measure the time that we measure with respect to us, an observer on the ground. We can reorganize each of these equations to solve for ta and tb first. So ta is equal to L over c minus v, and tb is equal to L over c plus v. Therefore, the total delta t prime is equal to L over c minus v plus L over c plus v. So we can actually combine these factors by multiplying c plus v and c minus v on the top and bottom respectively. So something like this plus L over c. And then we then obtain delta t prime is equal to 2lc over c squared minus v squared as the final simplification. But we can simplify this even further. So similar to what we did before, we can actually identify the original time that the clock would travel if it was at rest relative to us. So that would be delta t is equal to 2L over c. We can now take this out of our expression to get delta t prime is equal to 1 over 1 minus v squared over c squared delta t. This looks similar to what we had for the transverse light clock, but this factor here isn't quite the gamma factor. Specifically, this is gamma squared. So now delta t prime is equal to gamma squared delta t. What's going on? Well, if we compare this to our result from the transverse clock, we get that the delta t prime of the longitudinal clock, which I denote here with the subscript L, is equal to gamma times delta t prime of the transverse clock. So this contradicts Einstein's first postulate, which states that we should expect delta t of the longitudinal clock to equal the delta t of the transverse clock. Rotating the clock technically shouldn't have any difference. So the solution to this lies in another fascinating aspect of special relativity, length contraction. Length contraction is the phenomenon where an object moving at a speed relative to us appears shorter along the direction of its motion. In this case, it would appear that the distance between the mirrors would appear shorter. So let's take a look at how length contraction resolves this contradiction. Let's go back to our longitudinal light clock. When the clock is moving, the distance between the mirrors in the direction of motion appears shorter to the stationary observer. If the rest length, the distance between the mirrors when at rest, is L, then L prime is equal to L over gamma. And remember that gamma must always be greater than 1. With this into account, the light appears to have traveled less distance with respect to us, so that the light's travel time matches the time interval that we derive for the transverse clock. Delta t prime of the longitudinal clock now equals delta t prime of the transverse clock. So it looks like when we correctly account for length contraction, we find that the time intervals for both the longitudinal and transverse light clocks are indeed consistent with Einstein's first postulate. This additional factor of gamma in the longitudinal clock is exactly compensated by the contracted length that we perceive on the ground's frame. The light clock examples, both the transverse and longitudinal, illustrate how time dilation and length contraction are derived and interconnected. Understanding these concepts can help us grasp the full implications of special relativity and its effects on spacetime. So if you found this video to be interesting, don't forget to check out my other special relativity videos and subscribe for other physics, astrophysics, engineering, math, nerd VTuber content. And comment down below if you have any feedback or suggestions. Thanks so much for listening, and see ya in the next one.